okay. It's I think this semester I just want to emphasize on the fluid flow simulation and how to start to use the software. And to master it, you need time, you need practice. Okay, so I guess let's leave it to the future opportunity. You know, you have a chance to practice it. That would be great. Okay, so okay, let me share my screen. If you have any question, please jump in. Okay, and let's discuss it. Any question if you have. I don't mind and talk to something not I prepared. Okay, I like to discuss those stuff with you. Then help you understand. Okay. How many are we here? How many of you here? 29 total. That's not very good attendance. Huh? I heard you say you have 47 total students in the class. Okay. Okay, let me share my screen. Okay. Can you see my PowerPoint? Okay, good. Let me start presentation mode. Okay, that looks better. Okay, computational fluid dynamics. Okay, that's what we're going to do the rest of the semester. Okay, so let me give you an introduction first. What is fluid dynamics? Okay. Okay, so what is fluid flow? Okay, I choose to show you this picture. Okay, you know, and if you tell me what this picture shows. I feel this picture is a good representative for the fluid flow. Do you agree? Okay. First of all, did you see the airplane, the small airplane down there? It's a small airplane down there, right? Okay. So this is actually the wake, the fluid flow, the flow behind this airplane, which is taking off. Okay. So first of all, this picture tells you that the fluid flow is pretty difficult to study because it's invisible. Okay, why you can see this fluid flow now? They are doing a test. Okay, they put the smoke on. They put the smoke on when the airplane passed the smoke particle is so tiny, so light, it basically follow the movement of the air. When the small particle follow the movement of the air, then you can see it. You can see the movement of the air. Okay, so it seems like the first thing is fluid flow is invisible, especially the airflow is invisible. And you study it, even you're trying to see it, it's heck of a job, you know. You have to put a smoke generator down there, huge, you know, put red smoke there, let the airplane pass it accurately. Okay, then, oh, okay, vortex, okay. Okay, so this picture shows the flow field, okay, caused by the taking off airplane. Even a small airplane like this, it creates a circulation like this. Okay, so it's pretty much like a what? This is like a tornado, huh? Does it look like a tornado to you? Or maybe a hurricane, less strength hurricane, smaller, you know? All the circulation, all the vortex basically are the same, but the difference is between different vortices is the strength, right? If it's strength really, really strong, it's a strength really, really big, then it becomes a tornado, right? You know what tornado can damage, right? If the vortex becomes so large with the strong strength, then it becomes a hurricane, right? So, but why there the damage from the tornado or hurricane? Because of circulation, right? Circulation and the wind speed it created. Okay, wind speed. And you know, you have the fluid mechanics, right? You know, Bernoulli, right? Bernoulli relates the speed to the pressure. You know, speed and the pressure are related. You can have a stronger wing. You have a wing, it has speed, then there's a pressure related to it, right? Same thing for Newton's second law, force equal to ma. Your movement of the air will lead to force. Okay, so basically, so for you to study the fluid mechanics, okay, dynamics, which basically means the force and effect, right? That's called dynamics. So in order to study the dynamics, okay, you really need to understand the flow field. What is the movement of the fluid? Okay, you have to know the movement first before you can determine the force. Okay, dynamic is a subject that relates the force and the movement. Okay, that's the overview I want to give you a big picture. Okay, so in that sense, movement and the force are related. Okay, so you have to know one to determine the other. That makes sense? Okay, so that's why it's so important to first to see the fluid flow. If you don't even see it, what the heck? You know, what do you study it? You don't even know what the flow looks like. How do you determine the force, right? Force and the velocity are related. You have to know the velocity field. Okay, what's the velocity situation? Okay, what's the flow look like? Then you even have a hope to understand what the force it will cause, it will lead to. Okay. That makes sense? You know, it's dangerous to take off after an airplane. This one actually showed you. Right? You see, such a small airplane creates such a big vortex down there. Okay. So if you are the pilot behind this airplane to try to take off, do you want to fly your airplane into that hole of the vortex? I guess you don't want to. Okay. Create a lot of instability, and you might crash your airplane if you fly into a vortex, if it's strong. Okay, so why vortex? You know, it will have a negative effect on airplane after it. I think I mentioned in the fluids class, in the center of the vortex, does it have high pressure or low pressure? Anybody still remember?
Isn't it low pressure?
Yeah, it's a low pressure, just like hurricane. You ever pay attention to the hurricane forecast? Probably you did. Everybody did, right? Look at the Weather Channel. They talk about hurricane. They always report the hurricane center pressure. Is that right? Do you remember center pressure? What's the center pressure for Laura? Do you remember? Well, it's changing every day, right? But do you remember the lowest center pressure during the Laura? Probably.
Was it like 900 something millibars?
Exactly. I remember that. I don't remember the exact value. I think it's probably 920, 930-ish millibar. Okay. What is the regular atmospheric pressure? Do you know? Anybody? You need to remember those values. You know, you're an engineer. You need to know what is pressure 14.7 psi, right? That's the absolute value, right? But in millibar, right? Millibar is like a SI unit, right? It's 1/100th of Pascal. So I guess the atmospheric pressure is about 100,000 Pascal. Okay, 110,000, I think. That's atmospheric pressure in Pascal. So in terms of millibar divided by 100, it become about 1,010 millibar. That's a regular atmospheric pressure. Okay. So a category 4, LoRa, actually the lowest pressure, I think it reached to about 920, 930-ish. Okay, millibar. It's lower than actually the atmospheric pressure. Okay. So low pressure is bad, right? Low pressure in the center of a hurricane. This is the vortex. It's a small scale hurricane. You can consider like that, right? So it has a lower pressure in the center. See the circulation in the center become I. See, actually I see an I there. This is really a small scale hurricane. A hurricane is I, right? Okay, the I has a low pressure there, lower than the atmosphere. So if you happen to fly your airplane into sucked into the hurricane, into this vortex, it will create a lot of instability. When you go through the center, you experience very low pressure, but the surrounding has high pressure. It will push you. Okay, that's why when you fly airplane, you always heard the pilot say, "Hey, we experience turbulence." Okay, what turbulence really is? Turbulence are vortices. Okay, you feel bumpy because of the pressure variation you experienced. Okay, so I like this image. Okay, this is an experiment conducted by NASA. Okay, try to study the wake of the airplane. Okay, actually that was my first research I did when I came to this country. I think it's 98. I was in University of South Alabama. I did a research for NASA. Actually studied the wake of the airplane. We use a computer model. Okay. At that time, we use a code from NASA. It's a Fortran, written in Fortran. They wrote it in the 70s. Okay, the vortex modeling tool. Okay, nobody use Fortran anymore, right? I know how to do Fortran. Okay, so we study the vortex dynamics on the wake of the airplane. Okay, actually the study was published and used by Atlanta Airport. Atlanta Airport is very busy, right? One of the busiest, it's the biggest hub in the South. And they use that study to determine how long you need to wait, how long the next airplane need to wait based on the size of the previous airplane. Think about if you had 747 taking off, you're not gonna create a very strong vortices behind. You're gonna wait longer if your size is small, if your airplane is small. Okay, it depends on also the size of the airplane and the size of the airplane in front of you. Okay, they have a scheme to decide how long you need to wait. Okay, it's not like, okay, 5 seconds I go. Sometimes you're gonna wait longer, and sometimes you can go earlier. Okay, depending on the size of the airplane you take off before you. Okay, depending on how strong the vortex is. Okay. So I just want to use this example to tell you, hey, we need to study the flow field, study the movement of the air, and determine the movement of the air in a certain space. Based on that, the movement information, velocity, acceleration, whatever it is, based on those information, we can calculate or determine the force information, which is what all engineers concern. What is the force? Okay. So the software you're going to use serves that purpose. Okay. It can determine the flow field for you. Okay. Based on the information you inputted. Okay, so another example, similar. Okay, come back to like a car design, race car design, right? Yeah, some of you might be interested in the race car, right? Race car design. They two focuses, right? You want it to be stable, stick on the ground. You want to reduce the drag, right? Usually, if you can achieve that, this is a good race car, right? So to stick on the ground is the lift. You know, you have to have the opposite lift. You know, you don't want the car fly up, right? You want the lift is going downward, negative lift, to make it to stick on the ground, even with high speed. Okay, then you want to reduce the drag. Okay, so do you know what this experiment is doing? This seems like it's in a wind tunnel. Huh? They put a car in a wind tunnel and put in a block in the wind tunnel. What do they want to test on this? They put the smoke. Obviously, that the wind blow to these two objects. Okay, and they put the smoke on. What does the smoke show you? Can you tell the difference between these two objects? Anybody? Do you see any differences? Which one has a bigger wake?
The block.
I think the block has a bigger wake. Do you agree? I agree with you. I think it seems like the block has a bigger wake and the circulation area. Okay, a region that seems like a stronger vortices. You know, the car seems like, see, because of the shape of the car, you know, the streamline goes down. It makes the vortex actually in the relatively bottom region, and it's kind of like a strained, right, in this area. It's smaller, basically. Seems like the vortex structure is bigger behind the block. Okay, so educated guess, which one has a better performance in terms of, let's say, drag? Can you tell by looking at this? By looking at this flow wind tunnel result? Educated guess, which one has a better, smaller drag?
The car.
Obviously, right? It should be the car. Otherwise, you design a car, it's shaped like a block. I never see that, right? I think I saw it once, you know, a while ago. Honda has a SUV, like a Element, look like a block to me. But most of the time, you the car shape like this, right? It's better. So why do you think the car has a less drag than the block from looking at these two pictures? Any ideas of reason?
Maybe on the smoothness of the upper part?
Smoothness. Okay. Can you relate what I said here about the vortex? About the pressure in the vortex is smaller? And can you see the reason? Due to the vortex? I said the vortex region is larger, stronger for the block, right?
I have a confusion because when I look at the car, I don't know if the car is on or off because, you know, in the behind part you have a little gas getting out, so that gas.
No. It's not gas. It's not gas. It is a test in the wind tunnel. The car is not moving. This is the wind tunnel. Blow air from the left to the right. Okay. Along with the air, you give some smoke, and the smoke show the movement of the air. It's nothing to do with the emission from the car. Okay, Luis. Okay, and I'd like you to relate the pressure in the vortex to the drag. How does the drag formed? The drag is a pressure difference between the front of the car and the back of the car. Do you agree? Do you agree? It's the delta P, pressure difference. Okay, pressure drop, basically. It's the drag. Is that right? Okay. So in the front of the car, there's no vortex. Okay, so basically in the front of the car, a little bit down there, but mostly in the front of the car, you have a similar pressure. Okay, atmospheric pressure, basically. Okay. And there's a little bit of pressure variation from the speed hitting it, but that's okay. That same speed hitting it, so you have same pressure in the front. Okay, relatively same pressure in the front. But what about the pressure behind? Pressure behind, is it higher than the front or lower than the front? First question.
Lower.
Okay, it's lower than the front. That's why there's a drag. Okay, is that right? Okay, drag is from the pressure difference between the front and the back is lower. Okay, that's the drag. But why the back has a lower pressure? Anybody?
Would it be because there's a lower velocity back there?
No, it's not. Lower velocity will be high pressure. That's a Bernoulli. Okay, the velocity is about the same. How much in, how much out, doesn't matter that much. Okay, it might be a little bit change from place to place, but major reason for the low pressure in behind, just like I said in the here. Does it have low pressure in the vortex center than the surrounding? Everybody, you guys follow me? The vortex center has a low pressure. Wherever has a vortex, you have a low pressure. Okay, just remember this. Hurricane, tornado, whatever. You have a vortex, then you have a low pressure. Same thing here. You have a vortex behind the car. You don't have a vortex in front of the car. That's why behind the car, you have a low pressure regions here in the wake, lower pressure. Okay, front is almost atmosphere. The back is lower than atmospheric pressure. That pressure differences causes the drag. Okay, you with me? Okay. Now let's compare these two cases here. So which one has even lower pressure in the back? Whichever has a stronger, larger vortex field will have even lower pressure in the back. Okay, the lower pressure in the back, the bigger the drag it is. Because drag is calculated from the pressure difference between the front and the end, front and back. If both cases has similar front pressure, then the lower the wake pressure is, the bigger the drag is. Okay, the worse the performance is in terms of the race car. Okay, does that make sense? Did you see my logic here? Okay. The reason I want to show the logic is the reason I want to tell you why people do experiment like this. At least even without any digital measurement, you will see you have a smaller vortex region for the car, which indicate a better, smaller drag for the race car. Okay, so we do experiments serve a purpose. Okay, it's not just for a show or for a colorful show or something like that. No. Okay, it tells you the wake, and from looking at the size of the wake, and you can decide which one had the lower pressure and which one has the better performance. Okay, does that make sense, everybody? Okay, again, I want to use this example to show you how important to realize the flow field, which is invisible most of the time, invisible in fluid mechanics. That's the difficult part of fluid mechanics, right? You can see it, okay? Without seeing it, you have no clue, okay? So then I think the first step, you have to realize the flow field. The software you're going to use is just to serve for that purpose. You can realize the flow field to you. Then based on the flow field result, it can also calculate the pressure and the force for you, okay? But you have to realize the flow field first. Okay. Think about this in doing actual experiment, okay, to realize the flow field. The software you use is basically just doing experiment in a computer. Okay, you're doing the same thing like this in computer and to realize the flow field like this. Okay. Then you can start from calculation for pressure and force. Okay. No, you know, in 311 in the fluids class, all we do is, you know, calculate the pressure based on the velocity. Right? These are relationships we already have, but without knowing velocity, how do you get pressure, right? So that's the thing. So that's the process, okay? So you simulate. So-called simulation basically is to realize the flow field. Then based on the velocity, acceleration, then you can calculate the pressure and the force. Then that's it. That's all what we need as an engineer, okay? Is that good, everybody? So far, so good? I want you to have a good big picture of what is really fluid mechanics and how to study fluid mechanics. Okay, maybe it's useful for you in the long run, in the future, when you do your work. Okay. Okay. Yeah, that's it. So this is like a summary page here. So fluid dynamic commonly. So what method to study fluid mechanics? I already mentioned it earlier, right? So we have 3 different ways to study fluid mechanics, okay? Theoretical, experimental, and the numerical, which is CFD, computational fluid dynamics. Okay, theoretical, okay, textbook, you know, ENGR 311, right? It's a theory class. So we did all theoretical study for mechanics based on some equations, okay? And we can solve, you know. But let's say this, actually in 311, it's not really theoretical. It's just apply the solutions. Like Bernoulli equations, those are basically solutions from the fluid equations, okay? It's not really solving anything. You just apply a solution. Okay, so actually the governing equation is pretty complicated. The conservation of momentum in differential form. Okay, I will show you in maybe the future slides, but it's pretty difficult. Leave it to the graduate school, right? Solving differential equations. But undergraduate, basically, we just use the solution, or apply the solution. You know, the solution of the differential equation is the equation. right? I call solution, it's not just value, right? You understand, right? Okay, so theoretical is a way, but let me tell you, the governing equation for the fluid flow is very complicated and it's unsolvable. I will show you later slides why it's unsolvable. Only a very handful of the equation you can solve. A handful of application you can, use the equation to solve. Okay, you have to apply heavy assumptions, make the equation simpler, then you can solve it. So most of the time, no, empirical, right? What we do, some experiment measurement. So lead to the second method, doing experiment. Okay, if you can solve the problem, like the vortex problem here, in this slides or in this slides, there's no way you can actually solve it, calculate the flow field, no. Okay, so that's why we do experiment, you see? See that experiment, okay? If you have a good experiment, you can even measure the velocity at every point. Okay?
Question.
Yeah, Luis.
Do you use isoclines in order to measure everything on the spiral?
You want a what? What'd you say?
Do you use isoclines in
No,
order to measure?
measuring velocity, just wait for a couple of slides. I will show you how to measure velocity. So, but at this moment, I want to convey the idea is doing experiment is all about measuring the velocities. Okay, because force and the pressure can be calculated. Acceleration can be calculated based on the velocity. Okay, so doing fluid experiment, of course, you have to show it first, but without showing it, it's fine. Sometimes doing scientific research, you don't want to see it. I know what it looks like in the back. I really need to measure the velocity. Okay, so you have to have a sensor, PIVs, different method to measure velocity, not only on one point, on many, many, many points in this field. Then you can realize the velocity field. Then you can do the calculation for the force or pressure. Okay, so experimentally is very common to the method to use to study fluid mechanics, very common. Okay, but experiment has a lot of limitations. Okay, the first limitation is this: money, right? It's expensive sometimes, not everybody can do, and also the limitation is experiment. Sometimes you cannot to represent the real situation. For example, I always like to use that example. I think that's a good example. Paper airplane. I use this thing in my fluids class sometimes, right? Do you remember paper airplane? Can you fold a nice paper airplane? Most of you can, Caitlin, don't shake your head. You can. You can make a nice airplane. Everybody can. There's a online YouTube have the instructions. You can make a really nice airplane. Okay, fly nicely. Do you know airplane? This paper airplane actually is an experiment. Okay, that experiment shows, hey, it flies nicely, aerodynamically sound, stable. Okay, but listen, what if you make it 100 times bigger? Exactly the same shape, paper airplane. Make it 100 times bigger, 100 times longer, still that thing. Okay, longer, bigger, use the same paper. Will you still fly? Yeah, I guarantee you it won't fly. It won't even lift an inch, it will break. Okay, so actually, hey, think about this. This small paper airplane is an experiment, scaled experiment of the reality of the bigger airplane you want to develop, let's say. Okay, then the experiment works well, aerodynamically sound. But in the reality, it doesn't work. Did you see the problem? So how do you ensure your airplane work? that small scale experiment doesn't work. It tell me works, but see, the reality, it doesn't fly. So you have to test your full size airplane. That's what I try to convey here. When you do experiment, you have to do the same size, most of the application. Scaled model doesn't tell anything. Well, basically, it's garbage. The experiment for the scale model, many applications, some application is okay, but in many applications, it's not. Okay, especially the viscous effect is dominant, then it's not. Okay, so think about in the 50s, Boeing developed 747, for example. Hey, come on. You want people to ride in there, take the airplane, fly the airplane, you need to make sure it's safe. You need to make sure it flies, right? How do they do the test? You're not gonna do the small scale test. Doesn't work. Larger scale, do you have a wind tunnel that can fit a 747 there? No way. Not even half of the 747 maybe. Okay, see, that's a limitation for doing experiment. Okay, it will be, that's one of the limitations. There's many limitations. Okay, I'm just giving you an example, show you one of the limitations to doing experiment. Very expensive and very difficult to do sometimes. Okay, but they are actually still doing small scale. You really cannot fit the 747 in the largest wind tunnel in the world. You can't. Okay, they still have to do small scale, but they have to adjust something, make the Reynolds number the same. You know Reynolds number? You have my fluids class, you should know the Reynolds number, right? Reynolds number has to make Reynolds number the same. Think about Reynolds number is the size times what? Velocity divided by viscosity, right? Is that right? Or density times the size times velocity times divided by the viscosity. So if you want to use a small scale to ensure the same validity, you have to make sure the Reynolds number is the same. So the size become 10 times smaller. Then you have to play with the properties. You can't just shoot air to the airplanes to the test. You have to decrease the viscosity 10 times. Or increase the density of the fluid 10 times, which is not air anymore. Okay, to ensure the same Reynolds number between your scaled test and the reality. Okay, so they have to put the wind tunnel, shoot in very, very fancy fluids, you know, weird fluid, very expensive. Okay, so it's not easy, you know, spend a lot of money for in the airplane industry for the development. Okay. So yeah, that's why, you know, the airplane, you know, Boeing's still very successful so far, right? 50 years after they have the commercial planes, right? And they're very expensive to do, okay? Not everybody be able to do, okay? Only handful of the country can develop commercial planes, okay? Okay, so I won't try to convey here. Theoretically, only handful of the problem can be solved, unsolvable, the equation. Experimentally, very expensive, have a lot of limitations. But then what? We have to still study fluid mechanics, right? Then lead to the numerical, you know, especially when computer become powerful, okay? When computer become more powerful, then the numerical CFD, computational fluid dynamics, become more feasible and more realistic, okay, to solve fluid mechanics problems. Okay, so these are the three methods. So in our mechanical engineering curriculum, you experience all of them, right? 311 is theoretical, 312. Many of you in my 312 now, right? It's experiment for mechanics. Even in my class, I ask you to do the hands-on experiments, right? Video projects, Okay, then CFD is in here, MEN 330. Okay, so yeah, this course we're going to focus on here. Focus on CFD. Okay. Let me talk a little bit, since it's introduction, so let me talk a little bit about the history of the computational fluid dynamics. Okay, the CFD theory is there way before the computers. Okay, numerical method is there. It's called applied math. I don't know if you probably didn't take a applied math class, but I think probably if you major in mathematics, they have applied math or numerical methods. Okay, these are all the methods. Okay, it's the concept is similar to the calculus, similar to the integration. How do you measure an area under a curve? Remember this? Integration. Yeah, Luis, what'd you say?
Use the integrals.
Use integral. So what is the integral? How integral works? Actually is, remember in the first class they teach you integral. You divide the area under the curve into small rectangular elements. Remember that? Right? Infinitely small rectangular elements. Okay, but because it's rectangular shape, for each small element, you should be easily calculate the area. Okay, it's just dx times y. Remember? Okay, so what about you add them up? The area of all the small elements. The integral sign basically is a summation sign, right? Okay, you add them up. You have a area close to the reality. Depending on how small the delta x is. If the delta x take limit tend to be 0, okay, so your area is just infinitely close to the reality, to the solution. Okay, so this is the fundamental of applied math too. When you calculate anything, anything is complicated, it has a shape, you just treat it as a rectangle or treat it as a square. Okay, so it becomes linear on every small element. So if you divide into infinite number of small elements, you just add them up. Okay, this is the fundamental for the applied math. This is the same thing as calculus. Okay, 18th century, 19th century, they started already developing some of the model for computational fluid dynamics, although they don't have the computer. Okay, so if you divide it into 10 elements, you can actually hand calculate it, right? Although that result won't be good, right? If you divide it into 1 million elements, it will be closer. Okay, that's why I need a computer. Okay, but at early time, people do hand calculation. Okay. Oh, by the way, there are some image here, right? That's a famous one. You see the low cloud passing an island. This island has a mountain on there. Okay, that's image you definitely cannot see from bottom on the Earth. The satellite image, right? What happened with the wind, the cloud passing through the island? See, look at the vortices downstream. Can you see it? I see at least 4 of them. It's kind of like a vortex street. Okay, one by one. Okay, that's a famous one. Van Kamen vortex street. You know Van Kamen? He's a famous fluid mechanist. Okay, working Caltech. Okay, most of the stuff here, a lot of contribution in the early time, Theodore Van Kamen. It's a lot of contribution from him. One of them is the famous Van Kamen vortex street. It's flow over a cylinder or whatever object. Flow over it, the flow from the left to the right. In the downstream of the object, you will see the vortices. Okay, everything from mechanics eventually is vortices. Okay, here in that satellite picture, actually, we actually see that vortices von common vortex street when the cloud passing this island. Okay, so the theory is there, long time, hundreds of years. Okay, I think the earliest attempt to use the applied math, to use the numerical method to study a real world problem, it happened at 1922. Okay, a guy called Louis Richardson. Okay, he had a lot of contribution too. Some of the model we use named after him. Louis Richardson actually developed a numerical model, okay, mathematical model for weather forecasting. Come on, weather forecasting. That's the perfect candidate for CFD. Okay, the weather forecasting is pretty good now, huh? You see, they predict the trajectory of the hurricane, kind of accurate. And for the local weather, you know, within 24 hours, pretty good, not too bad. Okay, right? It is basically CFD. So I think the first attempt is actually for the weather forecast. They try to apply the scheme numerical model. Okay, so you have to divide the entire weather space, you know, over your city or town into many small elements. On each element, you calculate solving some linear equation, algebraic equation, instead of solving those differential equations. Okay, so that's a procedure. You divide it into small elements. So a lot of calculation, right? You have thousands of elements. So what they do is they utilize a factory of the workers to do the calculation. They reported 64,000 people. Okay, each one armed with a mechanical calculator. What the heck is a mechanical calculator? I don't even know what does it look like. I know abacus. In China, we use abacus, right? Old time. Here, mechanical calculator. This is way before the computer, right? So everybody perform some of the calculation. Okay, this example shows you the amount of calculation needed for the CFD. Okay, a lot of manpower because you divided it into thousands, if not millions of elements. So each element needs to independently calculate. Okay, so that's what they do. They have a leader in the center using color signal lights to telegraph communication or coordinate the calculation. Okay, they did 6 weeks of the work. Okay, then they try to predict the next 8 hours of the weather. 6 weeks. You know, after they did the 6 weeks, the 8 hour already passed, way past, right? So you can actually compare your result to whatever happened that 8 hour. It's a totally failure. It's the first attempt ended up a totally failure. It's wrong, you know, because so many calculations that are related to each other. Any of them made a mistake. Okay, any of the 64,000 people made a mistake. In the end, that error will be propagated everywhere eventually in the solution. So I highly doubt that only one people make mistake. They have many people making mistakes there. So eventually the result is terrible. It's really not right, correct. Okay, but at least that's an attempt. Right? At least that's an attempt. Okay. Then they try to apply the state-of-art technology at that time. It's not anymore, but at that time it's state-of-art. You know, never used it for a real application like this. They try to see. They always believe in math, right? People always believe in math. Math should be right, but human make mistakes. Okay, math can be relied on, but human cannot. So that's the history for the first attempt. It's bad, and then people think about it. It's too complicated, too many people. You know, it's not possible to even do those kind of larger scale similar calculation. So let's focus on a little bit easy one, simple one, small scales. So I think the first publication, 1933, is to study a flow over a cylinder at a very low speed. Okay, that's the easiest case you can do. But still, this is the benchmark case. People still doing, graduate students still doing CFD. The first attempt always try to do something simple. This is an example. 1933 published the result to show it's a successfully calculation of flow over a circular cylinder at low speed. The flow field look like this. I think this result is from the 1953 publication. Okay, show the vortex pair behind the cylinder. Okay. When I see this result, show this result. This is, although it's not, maybe not from computer, but still, CFD result is not the calculation for a value. It's calculation of many value in the space. You have to divide this space into many small elements. On each element, you need to calculate the one velocity. Okay, I mean velocity, not just speed. Velocity means the speed plus the direction. So on every location in the space, you calculate speed and the direction. Then put them together, you can create the field like this, vortex. Okay, one point is useless in fluid mechanics. You have the data on one point, mean nothing. You have to have a data on thousands of points. Then it can tell you the picture of the entire space. What does the flow look like? Again, that's this important thing I want to convey here. A single point value in fluid mechanics measurement or simulation, whatever, it's useless. Okay, you're studying a field. You realize a field, which is a space, a defined space. Okay, that's why you need many points. They call it a grid. Have you heard about the word grid or mesh? In the modern science, everything is into a grid, right? CFD, same thing. You have to generate the grid to cover the space of inches. Okay, then calculate on every point. Okay, so this is 30s and 50s before the computer become usable. It's basically hand calculation. Okay, a lot of manpower. Start from 60s, then the computer become possible. Okay, so they always start from the high-end research labs first. You know, like Los Alamos, you know, those places, like Stanford universities, or those places. They start to use computer first. Okay, the first few application the computer can run is applied math, numerical modeling, because the calculation is simple. It's just basically algebraic equations to calculate. No integration needed, no derivative needed. Just add, minus, multiply, and the division. Okay. The good thing about applied math is to convert the differential equation into the linear algebraic equations so that the computer can solve, although it's not exact solution, but it's at least some approximation. Okay, when the computer become possible, 60s, 70s, some of the early flow model has been developed. Okay, so early CFD models. 80s and 90s, then the personal computer become popular. Okay, I remember I have my first personal computer in the early 90s, very early 90s. I know that's very fancy at the time, a computer. Okay, but I think at that time in the entire world and start to have PCs. Okay, so then companies want to develop something for you to run on your PC, right? You have a PC, what to use it for? At the time, we don't have Windows even. Okay, right? So that they develop some of the commercial software at that time. It's all the popular software. It all started from 80s and 90s. For example, the first one, Fluent. That's what you are going to use. That becomes the dominant one, right? So, but they started that time. At that time, there are many different softwares. Only a few left right now. Okay, a lot of them disappeared and merged, you know. Okay, so I guess that's 80s and 90s. I show you Fluent, since we talk about Fluent. Again, see, that's early you can publish a paper by just realizing the flow over a cylinder, okay, in the 50s. So now in 80s, when you have Fluent, it's a piece of cake. You can easily simulate it like this. This is the result from Fluent, okay? So I want to introduce a way of display the result. This is called vector field, okay? So I guess in some of your math class, you talk about the vectors, okay? This is a powerful method to display the result. You can look at this. They have actually a lot of grid point, a lot of points in this flow field. Every location, every point, you have an arrow coming out, which means that at every point, the Fluent calculate a velocity for you. So you can realize that velocity into magnitude, the length of the arrow, and the direction of the arrow. Okay, so you have thousands of points. You put them together, use the vector field. You can actually show the flow field. Okay, does that make sense, everybody? That's one of the display method I want you to use in the future projects. Okay, vectors. Okay, but you need to know that basically it's a grid covering the space. On every grid point, it basically calculates the U, V, and W. Okay, so that you can make vector arrow. Okay, so that's a piece of cake, right? From simulation from Fluent. This is even higher Reynolds number than the previous case I showed. Previous case I showed, I think, have a symmetric. See, this is a symmetric vortex pair. Only happens when the fluid is really, really sticky, like a molten lava or bee honey. Okay, passing a object, it will be like this. If the Reynolds number is a little bit higher, the vortex become this kind of vortex shedding. It's not steady anymore. And one vortex coming out from the top, then that vortex will propagate in the downstream. Then another vortex will coming out from the bottom, and it will also propagate the downstream. Okay, so it's a fully transient process. That's called von Karman vortex street. Okay, with Reynolds number greater than 40 probably. Okay, it will show like this. Okay, so okay, that's one of the example. Fluent, okay, can do very easily, can be done in Fluent 90s. Another example I want to show here. Okay, what is this? A rocket. Okay, you can even study the aerodynamics of the rocket fly. Okay, you look at the space. I don't know what the value of this is. That pressure? It shows you the pressure field around the rocket when it flies through it. Maybe this is a kind of like a what, missile or something. Okay, whatever it is. Okay, and the most important thing showing from this figure is actually look at the surface of the rocket. You use the colors. What does the color mean? Color means those values. These are the contours. Have you know the word contours? Use the contours to show the values, right? Color contours. So each color represents different values, right? So usually by rule of thumb, by convention, red is high value, blue is low value. Okay, so yellowish is in between. Okay, so it shows you, hey, as a pressure distribution along the surface of the entire rocket. So this is really powerful information. Okay, when you design something, especially mechanical design, you design an airplane, for example, F-22, F-35, F-80, whatever you design in the future. You need to know the pressure distribution on your surface, on your plane when it flies, right? So in case some of the weak points, you have high pressure, okay? It's easy to break those points. You need to make sure, if you know it, you need to make sure you design better to enhance it, okay? So surface information, very, very powerful information for the designer. Okay, so think about this is a numerical test, just like you test in computer. Basically, you reflect the reality, right? Realize the reality. This is another example. What is this? Okay, this is another example showing how complex situation Fluent can simulate. Can I replay it? Kind of short. It's a video, okay? Fluent can, ANSYS Fluent can produce some video for you. Come on. It killed my processing. Okay, screen sharing stopped. Okay, I think my computer is too slow to run it same time as the Zoom. Okay, it terminated my PowerPoint even. Okay, let me reopen it. I guess I reopened it. Give me 1 second. Okay. Let's still go back to that slides. Okay, hold on. Let me restart my sharing. Okay. I guess I need to change my computer. Too slow. Okay, so let me not playing it. I just explain it to you. This is it's a simulation of particles. Okay, particle injection from an inlet to a chamber. Okay, to a room. Okay, so when you inject particle into a indoor environment like this, actually the motion of the particle is pretty complicated to calculate, to model. Okay, so terminate again. Okay, I can just talk here. So it's pretty complicated to calculate the movement of particle. You know why? Because the particle is light. It will follow the complicated flow movement, but also particle has its own weight and its own motion. For example, it will drop based on the gravity. It's not exactly follow the background flows. It's actually is a complicated combination between the movement of itself and as well as the movement, the background flow. Okay, did you hear about anything like a Brownian motion? Okay, those things. The particle, even without any force, it will still move by itself. Okay, okay. So and also it will move by the gravity. So it's not exactly follow the flow. So that's a sticky point for the flow for the fluid mechanical model. Is model the motion of particle. Always in the early years, it's really difficult. Okay, with the advanced models such as in Fluent, they implemented, so it's made it possible to calculate the motion of individual particles. So look at that video. You have thousands of particles here. Each particle has to be separately calculated to include the effect from the flow as well as from the neighboring particles. Okay, think about the how many computational power needed for realize those calculations. Very complicated. I just want to show you actually in the 90s and early 2000s, early 21st century, these are the state-of-art study to do the particle motion modeling. Okay. So that was actually my result. When I was a PhD student, we did a research project for Marine Corps. At the time, as you know, early 2001, 2002, there's a war against terror in Afghanistan, right? They have to deal with a lot of caves, you know. The terrorists hiding in the caves, you know, you need to make sure you get rid of them before you enter, you know. So they, whatever method they use, sometimes they put in some smoke in there to push those terrorists out. Okay, so but eventually when the soldier need to clear the cave, they need to enter too, right? You have smoking there. So what they do is they try to remove the smoke efficiently before they can enter. So you can't carry a vent or some fan with you, you know, when you do a mission like this, right? So, and also cave is, you don't have the outlet. Even you blow air to it, may not work as efficient as you think. So they invent something like they try to inject some nanoparticle aggregates. Okay, so they have a canister. You have those aggregates are not small. They have, it's a nanoparticle aggregate. So you have, they're made of small particles, but they together. Okay, they have a lot of surface areas. So when they collide with smoke particles, they can attract small particles, a lot of surface areas. So they can stick with small smoke particles very quickly. Then when those nanoparticle aggregates drops, it carries the smoke down. Okay, so it seems like it can remove the smoke faster, by using those nanoparticle aggregates. So at that time, the military want us to do some study how effective, when those processes. So we do experiment. We also do computer simulation. That's part of the simulation. We have to study the motion of those particles, different size particles, and the interaction between all the particles. Okay, so Fluent at that time, state of arts, right? Use that. Eventually, these are the published results. So it's okay to share with you. Okay, so my PowerPoint is terminated again. Okay, how many time do I have? When is the class end? 12:15?
12:15.
12:15. Okay. So I have 7 minutes. Let me restart my PowerPoint one more time. Let's skip that one. Let me restart my PowerPoint again. Skip that slide. So I just want to show you that Fluent is a very powerful software tools. Okay, all the bigger companies like Boeing, GM, Ford, they have certain modeling capability with the Fluent, do the fluid simulation. Okay, so it's very fortunate for us to have it at McNeese. Okay, so all students can use it. Okay, so I think that's pretty good. Okay, so. And it can really do a lot of complicated stuff. Let's skip this. Okay. This is in the early 20th century, 21st century, also one of the difficulty for flow simulation is, for the early time, you can only simulate the flow over a stationary object because you need to create a mesh. Remember, you have to create a mesh in the space near the object, right? For the flow simulation, to simulate the flow around this object. So mesh is pretty complicated to create, okay? So it could take some computational resources. But think about it. What about the object is moving? So at any moment you look at the object in the different space, it moves. So what? You body fit in the mesh, you have to create the grade every moment? Indeed, that's what early people do. Okay, the moment, the movement, every time step, very, very small time intervals. The object changes place, then you have to calculate a new set of mesh to cover the space around it. And then they make the calculation very expensive. Okay, very expensive. And in the 90s, you don't even have the supercomputer like us we have now. It's really not very feasible to do the movement, flow over a moving object. Okay, so the early development in the early 21st century is to my PowerPoint is still not turning on, so let's just talk for the last couple of minutes. So the early 21st century, people developed some mathematical model. Okay, so they changed the governing equation, to represent the movement of the object instead of changing grade during the simulation. So they make life a little bit easier for the modeler. So that's the early development for the 21st century. So that's a history. So now we use this for the virtual reality. Okay, so remember, you guys, a lot of video game you played. If you see a movement of the water, okay, those movement of the water in the video game, even it's CFD simulation basically. Okay, they can even make it really virtual reality from the CFD model, because the computational power is really advanced now comparing to the old time. Okay, I'll show you a couple of slides next. Okay, in the next class. I guess today probably it's out of time. Okay, so this is the history of a little brief history of the CFD. Next class, I will start the second half of the presentation, which is how we exactly the process we're going to take. What is exactly the process we're going to take in doing the CFD model? Okay, without even knowing how to run the software, you need to know the process. What you need to do first, and what you need to do second, third. What are the process of doing CFD? Then, when you using the software, you know, okay, I need to do this first. I need to find the button of doing that. I find the button of doing the second step, third step. Okay, so that's the introduction I want to do for Wednesday. Okay, it's a detailed process of doing the CFD. Okay, I have a couple minutes here. I can entertain any questions. Any question from you? Is that good? Exciting too. Yeah.
So like whenever they have those big air conditioners that whenever you're walking into like a supermarket or one of those big buildings that have like a AC unit on the inside of it,
Mhm.
do those block the flow, the air conditioning from like escaping, or how does that work?
So I don't know how does it work, but really that's a candidate for a flow simulation. Okay, you can create the supermarket space in computer. Okay, you place some air conditioning outlet in the space. You can model it. You can simulate the airflow. Okay, inside of this environment, indoor environment, inside this space. So if you know the movement of the air, then maybe you can answer your question, some blockage or whatever, right? Chris, is that right?
Yes, sir.
So I guess this is a good candidate for a model. Otherwise, you cannot tell. Hey, you're an engineer, you want to have some suggestion on the design or change. What's the base of your suggestion? Okay, your base is actually to realize the flow field in computer and to see what happens actually. Okay, if you see what happens actually, maybe you can have some recommendation on change, right? That's actually the purpose of this software, and the purpose of the CFD is to help the designer to understand the flow situation. Okay. Good. I think if you don't have any other questions, that's it for today. And hope you learn something today. Huh? And I hope you enjoy the rest of the semester to the end. Okay.
Thank you.
You're welcome. See you next time.
Have a good day.
You too.